But this evening we have Andrew Prentice, who is very local here, and been here I think for nearly 45 years, if I looked at the resume. So that's quite an achievement already that I definitely haven't been. So Andrew started off actually in Melbourne, but then at Melbourne University, did his undergrads there, and then did a PhD in Oxford. So he decided to move a bit further. And from there, with a short stop in the USA, he arrived early 1970s at Monash. And then Andrew worked on, well, the origin of the solar system. And reading your biography, it appeared it was mostly on the slightly smaller items in our solar system. So the moons, some of the discoveries you worked on. And then recently, now we got the dwarf planets. So I presume you will be telling us 45 years of adventures in the origin of a solar system and the dwarf planets. Andrew, please go ahead.
Thank you, Evert, for that very warm introduction there. And it is true, it's almost not quite a half century, but up to the 45 mark, I think next February, which was pretty well in 1972, was the dawn of the space mission to the outer planets. So my plan is to give you a talk tonight about the dwarf planets of the solar system and how they fit into the scheme of things. And that's Ceres on the left, that's the largest of the asteroids, and then Pluto and its largest moon, Charon, are on the right. And so that's what we'll be mostly talking about, and how they formed, and what the discoveries have been made. And the last year was a very big year for me because there were two large missions. There was the Dawn mission to Ceres, and then that was at the start of the year, March 6th, and then in July there was the much awaited arrival of the New Horizons probe at the Pluto system. So it was a very big year for me to sort of gear up for, and I've been thinking about all of these for quite a while. Well, I am at Monash University still, retired, but I do have a sort of adjunct position, professorship at the University of Southern Queensland, and that's why that's mentioned there. Now let me see if this slide facility works. It seems to be. I think I've moved to the second slide. This is the view we have of our solar system, a very planar. All the planets are pretty well in a common plane except for Pluto and Charon. Something's happened there. It's a collision of some sort. You can see the asteroids. And of course this is the sort of view the ancients had of the solar system. They could see out as far as Saturn. And last night, actually, though it was rather cloudy for us, all of those planets that were visible to the ancients were in fact visible in the sky, apart from the clouds. So the moon will disappear tonight, but that configuration should stay for a few days, with Mars and Saturn looking north and to the west, the other trio. So it's a very nice configuration. And beyond that's the Milky Way, which is hard to see from where we are, but that, of course, we're part of that, and of course we now know that these galaxies. We're not the only galaxy. There's M31, a very famous one, about 2 million light years away, and in fact the galaxies just spread right through the cosmos. And I won't go any further than that. I'll just stay, and I'll come back from there. And almost certainly within these galaxies there must be solar systems probably very similar to ours, and with this same sort of architecture. And that's the architecture that was pretty well agreed upon. Well, we all knew before the space mission, but there have just been so many startling surprises that often all of our early views have long had to be overthrown. And if you're developing a theory, it's very hard to sort of stay afloat and keep the ship moving, and that's what I've attempted to do over these last 45 years, made a number of course corrections. But the basis behind the theory, the modern LAPLACIAN theory, is what I'll be talking about a little further tonight. So this is the solar system we knew until about 2006. There was the IAU had their meeting in Prague. Unfortunately, Pluto was very proud of itself. It was its proudest moment. You know, it was the 9th planet. And then about sometime last August, 10 years ago exactly, it suffered a frightful indignity and was demoted. Similar to myself, actually. And something in common there. Yeah. And so now this is the new post-IOU symposium agreement. We allow now, of course, which is a good idea, Ceres is now actually called the dwarf planet, and Pluto, and actually a lot of guys beyond there, we'll come to them shortly, they're also called dwarf planets as well. In fact, right out there beyond the orbit of Neptune, you have the Kuiper belt, and there's myriads of icy asteroids in there, and it's objects from there that are probably Pluto probably was part of that originally, and that's the theory I've been working on. Somehow it had a collision and it got knocked inwards, and it even comes closer to the Earth than Neptune now and then. Let's look now, go back to Ceres, and this is the one. This is a very unusual. It's the largest of the asteroids, almost diameter of 1,000 kilometers, and it's an unusual object. It's very low density, a density of only about 2 grams per cc. So 25% of that object must be ice. Ceres was discovered by Giuseppe Piazzi back in the first day of the 19th century, and that was quite a. There had been Bode's law had suggested there might be a planet between Mars and Jupiter. There's space for one. And there was some early calculations suggesting where to look, and sure enough, he was persistent and he found it. And of course, all of these objects are named after Greek mythology, and this is a little graphic here where Giuseppe's obviously drawing inspiration from a mythological figure. That's not a lab assistant. It's actually a yeah, we'll come back to that. So for a while, that was, it was the only one, and there was no agreement what to call it. The Brits wanted to call it the Georgian, after King George, the Georgian star. And Piazzi, he wanted to name it after Ferdinand, the king of Ceres, Ferdinand, king of Sicily. So in the end, the agreement was to call it Ceres. And of course, in mythology, that was the goddess of harvest. And there are lots and lots of paintings there. There's one by a chap, Villiger, a Swiss painter, which is rather nice, I think. But there are many other murals. Here's one here that's a bit more fun, actually. It's I know that one has to. I was lucky to be in London last month at the National Gallery, and I didn't see this one, but there are certainly, shall we say, many more risque paintings, as it were, in galleries than this one. This is a nice little kindergarten job. So there's that was the lead up, and of course we didn't know much more about that until the New Horizons got moving, and that was launched quite a while ago, at least 10 years ago, and it's first sped to Vesta. In fact, this is the graphic I should have shown you earlier. It wasn't launched actually until 27th of September 2007, actually after the Dawn mission. That was 2006. And it had to get out there, it didn't have much, no sort of rockets on it, so it really had to rely on specially tweaked orbits and flypasts to actually get there. But the first place it got to was actually Vesta. Vesta is much closer to the Sun than Ceres. And Vesta may once have had a lot of ice on it as well, but it's been proven, I think this chap Larry Lebowski proved it, that at Vesta's distance from the Sun, if it did have an ice mantle, it would have long since evaporated. And you can see it's been really knocked around to have got to, it's probably had many collisions. In the lower half of that, you can see a mountain, and that mountain actually is about 12 miles high. And it's the head of a crater, a massive crater that's about 500 kilometers across, called Rhea Silvia. It's the largest of the craters, and it's a very, very prominent. And there you can see like a family portrait of how Vesta shapes up compared to the other asteroids that have been visited so far. The internal structure of Vesta has been deduced from the Dawn spacecraft gravity team, and they've worked out it probably has a small metal core and then a rocky mantle and maybe a sort of porous crust. You can see that blue area. And in fact, I have had a model for Ceres, for Vesta before it got there, and it was very similar in structure. My original model was homogeneous, but once they determined it had what is called a degree of central condensation. Now there may be a laser option on this device here, but I haven't quite mastered it yet. Oh, there, I have mastered it. That's wonderful. I must tell my wife about that. A new skill that I've acquired. Oh yes, this thing called the moment of inertia. We'll meet him later on. But if it was a uniform body, it's 0.4. It's obviously been differentiated, and so it's believed that it does have a metal core. And in my model, there is room for a lot of iron sulfide that's settled to the center, so that it sort of squares up. That's no problem. So there Vesta worked out reasonably well, and then we headed off to Ceres and got there last year. Now, I didn't realize this is a rotating one, but it certainly is. That's extraordinary. Steve, did you know that? Now, there are the bright spots. Every now and then you'll see them come by. I must have a very old laptop, I think. I didn't have those movies there. Those bright spots are really intriguing. It turns out they're really they're salt deposits. They're not like table salts, but they're sort of carbonates and sulfates. But you can see that they're right at the center of probably a fairly fresh crater. You can see its edges are quite sharp. And in fact, there was a paper published only just 2 weeks back by Maria Sanctus at one of the institutes of astrophysics, I think in Rome, and proving, in fact, that these deposits may have come from underneath the crust. Probably it's the result of a massive impact has come in and created a huge amount of pressure in that spot that we just saw a little while ago. And the pressure is shot down beneath, and it's pressurized the ice. And if you can melt butter by pushing a knife down hard. Well, the same with ice. It will melt under pressure. Obviously, the water has come up. The steam has come through the rock, and it's picked up these dissolved some rock materials to form those bright things. So that's almost certain there must be ice down there. But by and large, the planet, there aren't that many, shall we say, craters with sharp relief. You can see here, these craters are very, very, almost obliterated. They're very flat. That's called Kerwin crater in the middle there. It's about 250 kilometers across, but they're very flat. And this was picked up very quickly soon after the arrival there. There is a planetary society in America out on the west coast on Catalina Avenue. Not far from Caltech, and I haven't really met this person, but she's one of their reporters, and she noticed that it's incredibly flat and made the observation, geez, was it born that way, or did it become flatter in time? Now, as I said, the last 45 years, I just haven't been slouching, and a couple of years back, I actually published a paper, in that paper, I actually predicted, holy moly, the surface of Ceres will be very flat. So that was rather encouraging to see a result. Since people have reviewed my theory with suspicion, it's rather extraordinary that a suspicious theory should be successful now and then. Now, in fact, I was very pleased because I've known Chris Russell. He's the Dawn project scientist for a long time, and Chris had printed off a 3D model there. He's not offering me a cookie or anything like that. It's actually a flat. It shows how he should point it out. Geez, it's extremely flat. And so I was obviously pleased with that. And there it is again. And so then we come back to the question, why is it flat? What the heck's going on? And this probably, there may well have been that in the past, either there wasn't anything, or else if you got right at the bottom, maybe there was a subsurface ocean. And in fact, that's exactly what I had predicted 2 years back, that in the beginning all of the asteroids were ocean worlds. They were rocky, but they had about 5% of their mass was water, and eventually it froze. And of course, but while it was freezing, it formed a thin crust. But any bolides that came in, the big boys, and a lot of them at the start, they just go crashing through that ice crust, and water would flow out, and there'd be no trace of them. They'd disappear without trace. And you can see the moment of inertia factor I predicted down at the bottom, 0.295, is very low. And then I had developed this theory of why the asteroids, and we'll come back to that later, but at the orbit of the asteroids, it turns out the temperature is 270 degrees, just beneath the freezing point of water, but the rocks heat up through radioactive decay, and all of the early asteroids, although they're originally rocky, some of that rock is called hydrated silicates, and the water decomposes from the rock and rises to the center. So all those asteroids in the beginning had mantles of water, and they're all on a well-defined gas ring, and they're all moving around, and all of a sudden the little guys who have got there very proud of their little water mantles, but when they run into other asteroids, unfortunately, like little kids in the schoolyard, they soon get knocked over. And when they collide, like if you throw a wet tennis ball on the ground, it loses its water. So unfortunately, there was a cascade of water content. The little guys soon lost their water, and the larger asteroids, particularly Ceres, he finished up gobbling up, slurping up. That's called a slurp. It actually finished up grabbing all of that water, and it was a very greedy fellow. Even though he originally only had a 5% water bottle, he swiped all the water from the other ones. A very nasty trick. He should have been given many detentions after school. And it turned out he got gobbled up. 25% of his mass was water. So that's the theory I put forward. And that seems to fit in with what's going on. There should be a movie here. Now this is tricky. Steve has told me how to fire these movies up, and there's a way of, apparently you can, you've got to move the cursor here and do, ooh, listen to that. Jeez. That's Kerwin. Yeah, that's a very nice movie there that was put together by that fellow Chris Russell there. You'll see his name right at the end there. But it's Simone Marchi who's at the top. He's also in Rome. Which is nice, you know, Piazzi, well, I guess it was Sicily, but it's part of Italy these days. There are quite a few Italian guys there. So I should make a visit myself one day and visit is it called the Eternal City? I think so. Those the classical scholars will be present will know about that. Anyway, he was the one. I met him last December in San Francisco, and he told me about this amazing discovery. So what happens? It looks like there is water there. There have been observations made a couple of years back by a chap Koopers from somewhere in Holland. And he found that you could, this is an artist's projection, there's definitely water there, there's definitely ice there. And so this is what we think to be the model of Ceres. It's got a rocky core, very highly differentiated. Peter Thomas, in fact, observationally established this result about 10 years back in 2005. This object Ceres is probably highly differentiated, water-rich ice mantle over rocky core. And in my theory, that's fine. It started out with a watery mantle. Eventually, that watery mantle froze. While it was freezing, all the big bolides came in and sank to the bottom and left little trace. So that seemed all nice and squarely sorted away. rather unfortunately, about 2 weeks back, they published the first gravity result. And the moment of inertia was 0.37. But Andrew had predicted 0.295. Now that doesn't seem, you might think that's not far away, but I can tell you it's one hell of a distance away. It's there's no way that two ideas can be reconciled. That in fact, Peter Thomas's model is the same as mine. He had about 0.3 and 0.30. And this is a real worry. I think I thought I'd had everything sorted, and then you go down to the market and buy some apples, and you never know, and you find a bad one there. And so there, I thought, no, what the real trick is, boys, or everyone, that you can't tell these guys they've screwed up. That doesn't work in science. There must be something going on which we'll explain. We'll come back to why. So there's Park's result. Ryan Park, I don't know him, he's at JPL. By the way, that movie was made at JPL, and I've had about 24 visits there, and I know about 600 people there too. It's a really great facility, and that's where the Ceres and so anyway, Ryan reckons it did not differentiate. So the ice, it doesn't make sense with what's going on. They're completely different. And about 4 years back, I did give a talk in San Francisco, and I did make it very clear then that Ceres and Vesta formed in the same gas ring. Why are they so different? What has gone on? So that's Ceres. Let us now skip out, leave that to one side for a moment, and go out and look at Pluto. And as I said, there are a whole lot of dwarf planets out there. Pluto's not the only one. There is Charon and at least the moon of Pluto. Eris is the one that we had earlier, but there's a whole lot of those guys. Now Pluto, I think, is one that's perhaps we're all familiar with, and we'd like to keep it as planetary status. Charon, I think, in fact, was discovered in 1978 by a chap called Jim Christie. And I think at the time his girlfriend name was Charlene. He somehow wanted to call it that, but that wasn't allowed. It had to come from mythology. And I think Charon is a figure from the Greek underworld. So that was eventually that's where the name came from. Now here's the discoverer of that one, a chap called Clyde Tombaugh. He's gone now, but he discovered that in 1930. At the Lowell Observatory at Flagstaff, Arizona, and of course eventually he had a bit of a say, and it was called, actually he again didn't have a say. There was an English girl called Venetia Burney, I think, who only 11 years old. She suggested, her father was an astronomer, that it be given the name of Pluto. And Clyde was happy with that because the initials of Percival Lowell, who had founded that observatory, were of course the same as the first two letters of Pluto. So that's the Pluto system, and it's got Pluto and Charon, but in the Hubble spacecraft, about something like 10 years ago, again, everything seems to be 10 years ago, 2006. They found two more moons, Nix and Hydra, and interestingly enough, you've got the New Horizons mission that's got the same initials, like we're talking about Pluto. Now that was interesting. Now how did it form? How did that system form? Well, one theory was, and it was put forward actually. It was actually first suggested by Doug Lynn and another fellow Mignard from a dynamical viewpoint. Pluto once must have been a single body spinning very rapidly, and if it had been liquid, maybe it was going fast enough, it could have split apart and fissioned. And this model, actually, I've taken this diagram from a fellow called Wolfson, but it's a sort of graphic that shows that. Now the fission theory had originally been thought of much earlier by a chap called Raymond Littleton. He's a Cambridge astronomer. In fact, I used to know Ray. He used to make visits out to the Jet Propulsion Lab, and so several times I met him out there. He's been long gone now, and I did visit the Institute of Astronomy in Cambridge where he worked, and in fact this is a photograph I managed to get of him when I was there. He of course worked with Fred Hoyle. They both lived about the same time. Fred, I think, was born about 5 years after Ray, and similarly died. They both died about the mid-80s. But you know, Fred was a colossus of astronomy in Britain in the 1950s and right through that time. And this is Ray's book. And it was in Ray's book that he first studied the rotating liquid masses. And he came up, this is not his diagram, this is mine, but he had a little sketch of what would happen if fission did occur. Just as you spin the object up, eventually if it was liquid, it would adopt a sort of pear-like shape. I must admit that looks more like an avocado. But there's a reason for that. Ray, this is all my work here. In the beginning, I think what happened, Pluto was a very much larger object, spinning more rapidly, and it was an intimate mixture of rock and ice particles. And then there was a lot of radioactive heating from the decay of aluminium-26, and within about 100,000 years, the ice started to melt. And if that object was already spinning rapidly, as the rock settled to the center to form that brown core you see there, as the rock settled to the center, the moment of inertia would fall and the object would actually speed up. And my contribution to the subject has been, and I presented that last year in San Francisco, that the reason why Pluto fissioned was because of an internal process of sedimentation of rock particles which caused the object to speed up. And up to that point, the fission theory had been rejected because there was no way of understanding how you could spin up an object. But this is an internal mechanism, and most people seem to agree with that. And as a result, you do get two objects, and as Ray showed, the ratio of the primary to the secondary object is about 8:1. And that's exactly the ratio of Pluto to Charon. And that's been measured now. These are called GM values, but essentially they're mass. But if you look at these mass ratios, Pluto is about 860, and then that's 106. It's a ratio of 8:1. But that's exactly the ratio that Ray Littleton had predicted when you have a spinning body. What is amazing is that when I take Ray's work and then apply all the chemistry to it and take into account all the amounts of rock and ice, when it does split and you have these objects with a mass ratio of 8:1, the densities you get for them do turn out to be exactly what has been observed. You solve for Charon, and then after you've solved for Charon, you adjust the size of the rocky core. The material that's left over gives you Pluto, and the radius of Pluto and the density of Pluto that comes out of the fission theory coincides with what has been found. Now that hasn't been published yet. I mean, these are the observations of Alan Stern, but my ideas I'm telling you tonight are mostly new ideas, but I'm very happy to share them. And 20 years back, I did actually publish a paper in the Australian Journal of Astronomy, it's no longer, I think, available. But in that paper, I actually worked out what would happen with the fission model, and I did make a prediction there that beyond, this was 1993, that beyond Pluto, there may originally have been several other moons. There were several other bodies orbiting beyond Charon, but the paper was largely ignored, and although I did publish abstracts of it here and there. But in fact, 4 years ago, they in fact found these moons. There are several moons beyond Charon, and in fact, I had 20 years prior to that had predicted it. So the model, this modern Laplacian model, does seem to have the capacity. It does seem to have the capacity to explain the observed solar system, the physical properties, and it has the capacity to make predictions which are then subsequently confirmed. That's a much more difficult task to achieve than explaining something after the fact. In hindsight, it's much more difficult to make a prediction that's successful. Now, there are other theories. That's the fission model, which I said stemmed from work of Ray Littleton, and I've applied Ray's work with my ideas of the chemistry. But Bill McKinnon, he's out there in Missouri, he's long since promoted the what's called the fission model, the collision model or giant impact model. That is that in the beginning, Pluto collided with another object, and a bit like it's been suggested the way the moon formed from the Earth, this object collided with these two large bodies collided, and that the Pluto system formed from that. It's very hard to model that system, and it's very hard to make predictions. In fact, whatever predictions were made were that in fact there may well be myriads of moonlets around Pluto. And in fact, the NASA Dawn New Horizons team were really worried that if this collision theory were correct and all these shards were still flying around the Pluto system, then you know the whole New Horizons experiment could fail. And so it turned out that they never found any more moons that were first discovered 10 years back. What you had at the beginning is all there is. There aren't any others. So the collision model, I think, heads in the wrong direction. It's a very violent start. It's very hard to explain the chemistry of the moons and things like that. And, but nonetheless, it is commonly adopted that the entire Pluto system was formed from a resulting debris disk. But it's never really been properly spelt out why, and I never understood that. Anyway, it doesn't. I've just pursued my ideas and see how they pan out. The New Horizons mission, of course, is one that's been got to Pluto last year, and in fact, about July 14 was a lot of excitement there, and it was launched again, and I'm afraid another 10 years ago, and on an Atlas V rocket, and it doesn't really have much of its own sort of rocket power. It relies entirely on orbit corrections or going past planets and things. So it took advantage of going past Jupiter, I think. It probably tells you somewhere around there. Yeah, February 2007, soon after launch, the New Horizons probe got a big improvement in its speed from a process known as gravity assist. There's a slingshot effect whereby the velocity of a spacecraft can be rapidly sped up when it goes past a planet. And that's how it got it way out to Pluto as quickly as it did. This is a picture of where the New Horizons probe was a couple of days ago. And anyway, it got a big boost of speed going past Jupiter. It can't really alter its path very much. It has small little hydrazine thrusters that can give it a bit of extra boost, but by and large its orbit is has now been fixed after going past Jupiter. This is the system that was seen probably even a month before. It just shows how far away these objects are. Within New Horizons, that's the 29th of May, so like 6 weeks before it arrived at that system, then you see they were just starting to resolve those bodies. So we really didn't know terribly much. And in fact, here is a little graphic here, just sort of showing that's why it's called a binary system. And I'm just having a little trouble. My wife said I should get hearing aids. I've just taken it out now. I'm sort of getting this reverberation in my ear, so I've taken those out now. I'll try and keep my voice level up where it is. I think we've seen that graphic now. That reminds me of the Olympic Games. Isn't there something called a hammer throw or something like that? It's because Pluto's 8 times bigger than Charon. It hardly moves at all. and it'd be a bit unfortunate the hammer throw if the hammer stayed behind and the athlete shot off into space. But, yeah, that would be a bit grim. Here's a close-up. Oh, it's better now. I don't like that. Yeah, here we go. Now that's looks like a whale, the tail of a whale. That's the sort of the sort of famous sort of region, the sort of Tombra Regio, named after Clyde. A very unusual space, and I'll tell you why that looks like it is. But Pluto's surface is incredibly complex. It's mixtures of ancient terrain, very dark mountainous crater terrain, and very smooth terrain. It's a very complex world. And there's Charon. It's the largest moon, and you can see at the top there's a coloured region that's called the Mordor macula. They're not quite sure why it's so dark, but I think actually there's a reason for it. And then around the equator, you've got these great sort of chasms spreading right around. By and large, Charon is sort of generally smoother and less cratered than Pluto. And here are some of the smaller moons. They look like little jelly bean shaped things. And in fact, I think they originally, with the fission theory, these smaller moons, the primary, when the Pluto object fissioned, you had Pluto and Charon, but there were some smaller droplets. Ray Littleton thought that when an object split, you would get a primary and a secondary and some smaller ones. And I think these small moons were made up of just the smaller droplets that came away. They were spinning very rapidly, and they would have had an ellipsoidal shape and be fairly smooth too. There's some thought that this one may be a composite of two other ones. You can see it's thought maybe two of them have joined up. But certainly you've got that sort of jelly bean shape there. And this is Pluto, again, just showing how complex the terrain is there, extremely complex. And then in the what's called Sputnik Planum, in that sort of whale tail region, you can see all these funny sort of shapes and so on. These are thought to be convective cells. It's very cold there, and nitrogen condenses to form a liquid or semi-solid, and there's enough heat coming from inside Pluto to drive sort of little convective currents inside it. And then at the edge of that thing, you can see these are funny little mountains and things right on the edge. But it's thought to be nitrogen that's being convected. But there are these mountains about 2 or 3 kilometers high. They're almost like slabs of ice that have been thrown down, as if there'd been some massive eruption that occurred, and these were thrown away from that site. And then there are mountains, as I said, all the different colour zones. And here's this another one, a sort of like a snakeskin. It's a very complex surface. Here's there are all these things. Now, somewhere, there's meant to be a movie here. Now, this is going to be a big challenge for me to see if I can fire this up. Now, if all goes to plan, if I press, oh, was there a sort of noise? Yes. This is called a movie, and oh, it's shocking. Steve, that worked without. And we're looking down from the North Pole right across this icy region, and you come into Sputnik Planum eventually, where it's so smooth, and you get those convecting nitrogen cells. But look at all those slabs, as if they've been thrown out in some way, and there, yes, you can see that, and it's a great basin there that's filled up now with nitrogen. In the beginning, it would have been just empty, but it's all nitrogen gas. There's probably a lot of water ice there and mountains. So that's a very complex region. The surface is constantly being replenished, and that's probably why there are no craters. But you can see a bit of a mountain sticking up there. There's a lot of methane there on the peaks of mountains. There should have been a lot of methane there. And there's also water ice too. It's thought deep beneath the methane ice and nitrogen ice, there is a lot of methane. And in fact, what I'll be telling you later on, well, we're not too far away now, this is no coincidence. This, I believe, is the rupture point when Pluto fissioned. Charon, the great globe of liquid, burst through Pluto's outer shell, a methane crust. It was about 10 kilometers deep, and this fluid went off into space, and then the surface closed up, and those mountain-like objects you saw were in fact fractured slabs of the crust that was thrown out to one side and then fell back higgly-piggly on the surface. And you do see the methane that on the peaks of those things, and I'm almost 100% certain that the reason for this fishtail is that was the rupture point for the fission that took place. I haven't published that yet, but that I'm pretty certain is the explanation for that whole region. It's a very complex planet. It's got hazes, and of course it's got its moons, and how it formed is as I said, right at the is it one of these Kuiper Belt objects. That's how the system formed at very low temperatures where there's lots of methane and things like that. There's no actual nitrogen there at that stage. That's a gas which is captured from the nebula. But I did use my model to predict the composition of Pluto. This is its composition, and this object then split apart, and the crust of Pluto is made up of this methane ice, about 5%. That sort of comes out of the model. And that's where this model I have came from. And in fact, it does seem to explain when I solve for the amount of rock, because we know what the density of Charon is. Its density is 1.7. I use that result. That enables me to work out how much rock had settled out. It turns out about almost half of the rock had settled out to the center to form Pluto's core. And when that amount of rock had settled out, at that point it was spinning so rapidly that the object fissioned, and it burst through that region where the whale tail is to form that globe. And then later, Charon would have been in a pretty wild orbit. Eventually, Pluto and Charon, through tidal interaction, they now face each other. They're keep perfectly the same distance. But in the beginning, the orbit would have been quite chaotic. But what is extraordinary is when I use my composition that comes from my model, which had been published several years earlier, when I use that composition to pin the mass of Charon down, the density of Charon, whatever is left behind, the density of that globe and the radius turns out to be 1187, which is exactly the radius of Pluto. So it's really an extraordinary achievement of this modern Laplacian model. And that's Charon. It was once a great globe of liquid with rock at its center, and then a frozen mantle of dry ice, but surrounding that was pure water ice. And back there in early last year, I did predict that all of those moons of Pluto would be balls of pure ice, and their surfaces should be flat and consist solely of water ice. And in fact, I presented that at the conference, and in fact that has been confirmed that it is water ice. But what was also confirmed in February was it now seems almost certain that these chasms here have been produced through the expansion of, when water freezes, it expands. And it suggests now that in the beginning that really Charon once was a globe of liquid, as I had predicted back in 1993. These moons also would have been liquid worlds as well, and very smooth. Of course, over the eons of time, something like 4.5 billion years has elapsed since that system formed. And over those billions of years of time, there are lots of, the Earth gets hit by rogue asteroids and stuff. These objects would have suffered quite a few hits, but they still, particularly this object, still retains, I think, it has very few craters and still retains its primordial shape. You can see there how crater-free it is. The others, and this one has an unusual shape too, a bit like a dumbbell, that one over there, Kerberos. And this was the most important result for me, because the infrared spectrum from the New Horizons has definitely confirmed that there's no other material on those moons other than pure water ice, except at the pole. And I believe this red pole of Charon, which is the cold part of the object, when that liquid bursts through the crust of methane, almost certainly some of the methane solid would have been entrained in the liquid, and methane eventually is lighter than water, and it probably went to the top and most of it evaporated away. And initially Charon may have had a very thin layer of methane which evaporated away, and these other ones, in fact, these are called tholins. So they're complex hydrocarbons. So I think they are a testimony to the origin of that planet. So those are the results so far, and you can see the model has explained much of the data. What I haven't given you is a quick background of how the model works. And all my theory has been built up on Laplace's nebula model for the formation of the solar system. Laplace proposed in 1796 the Sun was once a huge spinning globe with size bigger than the orbit of Neptune, and as it cooled down it shrank inwards, and as it shrank it conserved what's called rotational momentum, angular momentum, and it proceeded to spin more rapidly, and Laplace conjectured that the primitive Sun would have thrown off rings of gas, individual rings of gas, or liquid he called it, and the planets formed from these. And the theory did seem to explain the architecture of the solar system at that time. Eventually, of course, people looked at the theory more closely, and they realized that if the cloud had to give up its angular momentum shedding mass, it would have probably had to shed most of its mass as it contracted in. So you'd have a planetary system which should be much more massive than what we see today, which isn't the case. The masses of all the planets is only 1,000th the mass of the Sun. And my work in the 1970s stemmed from my supervisor in Oxford, Dirk ter Haar. And I was in Oxford last month for the 50th celebration of my college. In fact, I'm wearing the emblem of Wolfson College. I, in fact, was the very first graduate student of Wolfson, and they were quite keen. I arrived there in 1967, and I did my DPhil and also became a junior research fellow. But it was ter Haar, where I worked in the physics department, who suggested supersonic turbulence. And in fact, he suggested that Laplace's theory could be brought back to life again if you put in turbulence, because a collapsing cloud, the way that the criticisms led to its demise was that it lost too much mass. But if a cloud was very centrally condensed and had a low, there's a moment of inertia again, it is possible for a cloud with very low moment of inertia to give up its angular momentum at the expense of losing very little mass. And very like if you have a sort of spinning flywheel, even though it's very massive, if all of the mass is at the center, you don't need much of an effort to slow it down. And that's why a flywheel on a boat, all the mass is at the edge, because if all the mass is at the edge, it has a high moment of inertia. So Jeans recognized that a cloud with a low moment of inertia could give up and create a solar system like we see today, but he didn't know the mechanism. And it was Dirk ter Haar who suggested that I put in this concept of supersonic turbulence in the 1970s. I think the first paper was published in 1973, suggesting that in addition to normal gas pressure, there was a turbulent pressure, which was many times larger. And this turbulent pressure was driven by buoyancy. It was only effective in the outer layers of the cloud, and it pushed those outer layers outwards much more than the inner layers, and it caused the cloud to become very centrally condensed. And you can see there's that moment of inertia. As you add in the turbulence, the moment of inertia declines rapidly, just as Jeans had sought, and you get a spike at the edge because all the turbulence dies away, and you get a very dense shell of material at its edge. And when the cloud with a dense shell starts to rotate, that shell slips down to the equator to form an equatorial belt. And when you model it, the whole cloud, as it contracts inwards, develops this very massive belt at the edge, and that's the Neptunian belt. You're looking at its side on, and a gas ring is left behind, just as Laplace had conjectured, and then another gas ring. And it all comes about because of supersonic turbulence and because there's so much mass stored at the edge. And it takes a huge amount of, when the cloud sheds a gas ring, it's very disruptive. It has to rebuild pressure at its edge. And the process of extruding new material to the edge under conditions of constant rotation shuts down the angular velocity. And so the turbulent cloud sheds its angular momentum in discrete amounts. And I've had a student who modelled this. It does seem to be right. We were able to recover what's called Bode's law that gives the ratio of one planetary orbit to the next. It's a geometric formula. The formula tells you the masses of the gas rings, and you can actually work out that it squares up with what you see. But the most exciting result is that the gas rings have the natural capacity for focusing solids into a well-defined orbit. And beyond, in the more distant regions, the rocks settle down, the gas is moving slower than the Keplerian speed because the gas has to obey the laws of hydrodynamics, and the rocky particles shift in. The inner regions of the gas ring are moving super Keplerian, and once any rocks settle out, they moving too quickly for a Kepler orbit, so they move out, and you get a natural focusing. And that's why the planets formed in these well-defined orbits. And the temperatures too, there's a well-defined temperature law. There's 1 over R. And it's that law which allows you to work out the temperature at which Ceres formed, 271 degrees, just below the freezing point of water. So I think that's what happened, that Ceres did, although it doesn't have any native ice, it has a lot of what are called hydrated silicates that contain water. And when it heated up and got rid of that water, it turned out that it had an amount of water of about 5%, making up something like 4.2%, and had a density of 3.2. But that's, unfortunately, Ceres' density is 2.1, and that's what led me to believe and put forward that theory I showed you earlier, that Ceres has been a villain. In its infancy, it was a bully in the schoolyard, and Ceres accreted all the water dislodged from the collisions of smaller asteroids. All of the smaller asteroids started out as water worlds. They were very proud of themselves. But then Ceres went along, a very nasty fellow. With its superior gravity, eventually gobbled it all up. And that's where it got its water. And that's what you see today. That's my prediction for the structure. And the only fly in the ointment is my moment of inertia is 0.295. But Ryan Park, he reckons it's 0.37. And we can't both be right. And also, so that's the model that Thomas put forward and I agree with. So what's going on? These authors suggested, that Ceres didn't differentiate, and that's why it has a high moment of inertia. So something very screwy is going on, and I think what's going on is Ceres is itself. It doesn't have to be pushed around by Prentice. It doesn't have to be pushed around by Ryan Park, or NASA, or Monash, or the University of Southern Queensland. It calls the shots. And we have to figure out what's going on. I think Ceres did start out as a water world, but, and this is the key bit, and I only found it a week ago because I've been worrying about this for a long time. If Ceres did start out as a water world, and it did have a rocky core, and that rocky core had formed before Ceres had gone around the schoolyard stealing other people's water bottles, that core may well have looked like Ceres and been spinning very rapidly. Now, we know that Ceres spins rapidly with a period of 5 hours. Now, I think if you went inside Ceres and you looked at its core, it would have a very distorted core at its center, corresponding to a period of 5 hours. Today, Ceres spins with a period of of about 9 hours. And what happened, the core was spinning rapidly, the core had an oblate shape, but then it swallowed all this water unexpectedly from all different directions, and eventually Ceres realized it had a problem. It had a fast spinning core, but then it had this mantle of water which may have had less angular momentum. Eventually the whole thing froze, and the period we see today is the composite angular momentum. So we are probably, if you could look inside Ceres today, you'd probably find it does have a rocky core, and that rocky core is oblate, and it pushes the ice out, and it gives Ceres the appearance of being a homogeneous object in much the same way as a small satellite of Saturn called Enceladus. It has a homogeneous shape, but NASA has proved that it's differentiated. So what's really going on here is that there's nothing wrong with Ryan Park's work, but he's assumed the whole object is in what's called hydrostatic equilibrium. But in fact, this is a frozen, what we have inside Ceres is a great rocky core, which is not, there's no way the weight of water is going to alter its shape. And so this idea is one I'm telling you now, hasn't been thought of anyone else, but it allows a common explanation of why Ryan Park looks at Ceres and sees it as a homogeneous body, because he's assuming it was all once uniformly rotating, when in actual fact, if you look back in the past and see that Ceres had a water mantle, you can add in a different sort of core. And I think there's a lot of work to be done, but I think that resolves the problem. So Vesta may well have a core inside it. Now I just want to end the talk now because I'm almost out of time. I've covered a lot of ground, probably much too much ground. I was just going to, I had sneaked in a couple of encore slides. One was to tell you that I think that great whale tail was how Pluto had formed, and the other one, we're starting to look at other stars now, and we're looking at other planetary systems, and a lot of them do seem to have a shape very much like what Laplace had suggested. And it's just been recently announced, it seems almost certain that where we see the gas in these systems, that's where the dust is. And the only way that could have happened if this object had formed from a family of gas rings over a very short period of time, well below 1 million years. And that's exactly what the gas ring theory does suggest, that the whole solar system formed in a very short time from gas rings. So it's my belief that all of the ingredients are in place to consolidate this modern Laplacian theory, but the physics involved, as we've seen tonight, is absolutely monumental. There's just so much coming in, and you've really got to sit back, and it's a bit like solving a jigsaw puzzle in the dark when there are some missing pieces and pieces that are put in from other puzzles. It's a very nasty little trick. And I've got grandchildren. It's bad enough me trying to do the simple puzzles with them, but imagine yourself trying to do one in the dark. Now, ladies and gentlemen, Andrew is going to stop at this point. Thank you.
Andrew, thank you very much for this very interesting and enjoyable talk. I think we have time for a few questions. We have a microphone running around, so...
How did planets manage to clear their orbit? Because they would have to travel faster than everything in that orbit to clear it.
Oh, well, there's no clearing of orbits in the modern Laplacian theory. That's a feature of the disk model. If you have a disk, then the planets, they do have to clear their orbit. But with the modern Laplacian theory, you have a gas ring. It's all co-moving. It all has the same speed, and the little rocks condense out of the gas and they settle down onto the mean orbit. They're all moving together, and eventually when you've got a gas torus, and then at the center of that you've got a very compressed slurry of sediments and rocks. Once those rocks become sufficiently close, they start to feel their self-gravity and they draw together to form clumps and planetesimals. And I had another PhD student, Kerry Hurigan, showed the planetesimals would very quickly get together and you'd form a core. And in fact, the modern Laplacian theory, I had to skip over it, was Bode's law. But in 1973, I predicted that each of the four outer planets formed from gas rings of about 1,000 Earth masses of hydrogen. 1,000 Earth masses of hydrogen has 15 Earth masses of rock and ice. And so the first stage of the formation of the giant planets was the accumulation and rapid accumulation of a core of rock and ice of 10 Earth masses, or 15 or thereabouts. And once that core had got together, it could then grab the gas. But there was no clearing going on. These guys, they were on a well-defined mission. They had to form a core and grab the gas. Now, as Fred Poyle pointed out, as you go out beyond the orbit of Saturn to Uranus and Neptune, the hydrogen all the while is escaping. And although Jupiter and Saturn successfully captured much of the gas of their respective gas rings, by the time Uranus and Neptune got their cores together, much of the gas had gone, and they were just left high and dry, mostly as made of heavy elements. But Jupiter and Saturn would have formed large gaseous envelopes, which in turn would have contracted and themselves spawned satellite systems in exactly the same way as the planet spawned the sun formed the planetary system. And that's over the last 40 years I got involved with the Voyager mission and Galileo and Cassini, and used those missions to test the gas ring model. So it's an excellent question that you've posed. If I was a disk man, and I would be worried, scared about that. But I'm a gas ring man, and I don't have to worry about that question.
But if there's a gas ring in each planet's orbit,
yes,
everything's only one planet in each orbit.
That's right.
Why aren't they all like asteroid belts?
Oh,
just
good. Good.
Just accreting
good. Excellent. Another excellent question there, because planets like Jupiter and Saturn did successfully accrete all of their material. There's not much left over out there. But Jupiter, in the modern Laplacian theory, the outer planets form first. Neptune ahead of Uranus and ahead of Saturn ahead of Jupiter, and Jupiter ahead of the inner planets. And what happened? Jupiter, once it formed, and then the Sun contracted further and contracted another gas ring. You had all these asteroids going around the ring, and then you had Jupiter on the prowl, going around as well too, stirring them up. If you have a fox going around a chicken yard, geez, there are a few feathers flying. Well, that's exactly what happened with the asteroids. They wanted to get together, and Jupiter kept stirring them up. And by the time they went through the initial phase of forming planetesimals, and they got to almost the formation of forming a core, but finally, they had to give up. It was just hopeless. But then you come to Mars, which is quite stunted, or at least its mass is only 1/10 of the mass of the Earth, because even Mars had been hassled by Jupiter. And Earth, I think, is sufficiently far away from Jupiter's influence. It can just tell Jupiter to buzz off. But certainly Mars, it's survived. But all of the stuff that was left over, there was a thing called the Great Heavy Bombardment. Probably after 400 million years, there's still a lot of crud flying around, and eventually the Sun entered what's called its pre-main sequence phase. The Sun became very, very hot, and it started to erupt, and all sorts of winds going out. And I think a lot of the initial debris was swept away. But you're slightly taking me out of my area of expertise there. But it is generally believed the early Sun became overluminous, and a lot of the crud got blasted away. I've presented a very good spin on my work tonight. I should be a car salesman or something like that. The thing is, I have tried to bring the major problems out into the open tonight. And for many years I've worried about Ceres and why it's so different from Vesta. And I've put forward a model I think that will hold. And also for Pluto, whatever was achieved with the fission model and the work that was done by Littleton, and I forgot to, there were many giants before Littleton, not in the sense of Goliath. Newton We haven't mentioned Newton tonight. Normally I would. Isaac Newton. I was lucky enough to go to Cambridge last month and to visit Trinity College and have in the chapel a marvellous sort of statue of him up on a pedestal. I sort of positioned myself near it because, as many of you know, you can't see the whole story. You can only see part of the story. You have to make the best of a bad job sometimes. Barry. Yes.
Just one question, change the subject a bit. Mike Brown and his cohorts who think they've discovered this ninth other planet,
yes,
20 times further out from the sun,
yes,
and 10 times the mass of the Earth. Is that still a theory? How does that fit in with your theory?
I'm not sure whether there's been a hint of something there. Yes, yes. I don't know whether it's been confirmed yet, or it's a very frantic search going on to find that. And that Pluto was the ninth planet, unfortunately became a dwarf, and hopefully this other one will also prove to be a dwarf. But it is a long way out. It could be an interloper. I mean, stars, they pass through the Milky Way with a lot of material there. Bill McRae often suggested comets come from there. So once we've got firm data, Barry, now Barry, I should say, is a former president of the Astronomical Society of Victoria, so his questions I really have to listen to very, very carefully. Are you happy with that one, Barry?
The results of New Horizons seem to work pretty well with your model. Do they work negatively against more conventional models, and do you think that the LAPLACIAN model will gain traction as a result of New Horizons mission?
Yeah, I mean, there are features of the disk model that have proved to explain a lot of things. There's a chap, Morbidelli, in France, who's led this group, who've studied the influence of, how it's all dynamical, entirely dynamical. And there certainly are, the architecture of the solar system, or a lot of facets can be explained faithfully by Morbidelli's, it's called the Nice model. And, but they have never ventured into the chemistry of the solar system. And I saw many years ago that, and there was a very nice fellow, Peter Godfrey, in chemistry, who's long gone. He was so helpful to me. He got me, as I didn't like chemistry, and I gradually had to bone up on it. But I believe there's such a wealth of information just coming from the non-dynamical aspects of the solar system. Those are the ones I've relied on heavily. I have been successful, like predicting some moons around Neptune in 1989 that were discovered, and around the planet Uranus, and also these extra moons of Pluto. But I think, although Ray Littleton had never worked on Pluto, it's true to say his fission idea was the precursor for suggesting those. So I think that's why I give full credit to Ray. But time will tell. At the moment, I've come through a big, last year was a really big one for me with those two dwarf planets. I seem to have come out of it reasonably well, a few bruises, but reasonably well. As far as I can make out, there haven't been many predictions coming from Morbidelli's group about those two objects. I believe the collision model really has to do a lot more work to explain what has been found at New Horizons. The collision model had anticipated myriads or ensembles of extra satellites, but they never found them. If you read that science paper, it says no new satellites were found. And there are other features as well. I mean, the collision model is one that is a big group of followers of that, because it comes from the study of the Earth's moon as a collision model. And those guys, you know, they've put so much investment into it. And once you've invested a lot of time, you know, you don't want to see it slip away. At the moment, if you look at the raw data, it would seem that this modern LAPLACIAN theory, despite the questions surrounding its basis of supersonic turbulence, does seem to be very promising. And even my worst critics have, you know, grudgingly admitted that I am onto something. That's like a rocket, yes. Thank you all for bearing with me. It's sort of, sometimes my earlier talks have been a bit more jestful, but there was so much to cover tonight, and I wanted to have a more serious approach, so I think that was the correct thing to do. Thank you.